So good afternoon, everybody, and thank you for coming. Welcome to session 4B, which is instrument testing and analysis. We'll have 6 talks. I've been told that I should be severe with the time, so after about 10 minutes, I'll make some signals. After about 12 minutes, it'll get rough. Anyhow, we have 6 really good speakers today. The first is Carlo Sasso from Torino, the Italian National Institute for Metrology Research. And he will talk to us today about the Mass Emulator, a functional testbed for the GRS front-end electronics.
Okay, you can hear me, yes. Good afternoon, everybody. I'm Carlo Sasso. Thank you for the presentation. This is the small group that is working on what I will present you today, the Mass Emulator. Me and Christian with a greater effort, and he will present also a poster in the 6th session, I think. Okay, so since probably you don't know very well my institution, I will spend a few words. So INRIM is located in the northwest of Italy, so in Torino. It's starting northwest of Italy. It's as Bill was saying, it's the National Meteorological Institute. So in order to understand, it's like we are the Italian version of the NIST in the US or the PTB in Germany, only to mention two of the most known. We are providing standard and disseminating the units, and thanks to our state-of-the-art measurement capability, we support also science and technology in different way on different fields like quantum technologies, material science, and space, only to mention a few of the activity that we do. Today I will present the Mass Emulator that will be a ground checkout system for the defects and the front end electronics. The Mass Emulator will be between the real-time simulator that will provide by means of capacitance models all the capacitance of the GRS, and we will provide the electric signal to the front-end electronics in order to emulate the position of the test mass. The other task is to provide a conversion from analog to digital of the voltage actuation voltages. Okay, so the Mass Emulator the idea is that it must be, the GRS must be unplugged and plugged into the TME and the electronics should not recognize this change, so it must be completely transparent to this change. In order to provide an emulation, if we here have the capacitive bridge that is measuring by capacitive sensor the position of the test mass, in order to emulate, we will provide the current in the differential transformer identical to that will be produced by the GRS. What we have to do, and what we decided to do. In order to provide this differential current in presence of a variable voltage, we can do two things. Or we can control the voltage and keep constant the capacity difference, and this was done, for instance, in the case of LISA Pathfinder. In our case, we do something different. So we don't do an electronic emulation, but we will do physical change of the capacitance as is happening in the GRS. So we will have a constant amplitude voltage, and we will change the capacitance. Okay. So in the GRS, as you probably know, we have 12 electrodes surrounding the test mass, and they are measuring the position and the rotation, so the translation and the rotation of the test mass inside the GRS electrode housing. We will provide 12 electrodes as well, but we will organize them into six couples. And in this cartoon, I will show you the idea that stays behind what we are designing. So these are the coupled electrodes, and they are connected to linear actuators. So in the TME, what happens is exactly the opposite that what happens in the GRS, in the sense that we keep the test mass, the yellow bar here, fixed, and we move the electrode around in order to copy what is happening in the GRS. So, for instance, for a pure translation in this direction, all the electrodes are a set of 4 electrodes. And here I am representing only 4 couples of electrodes, and 2 couples are missing because we are describing only the X and Y direction. So when we have to emulate this translation of the test mass, all the electrodes are getting closer to the test mass, and on the other hand, when we have to emulate a rotation of the test mass, they are moving in a differential way in order to emulate the rotation. Okay, this is a design of the test mass emulator. So we can see that we have chosen to have sizes of the electrodes and of the gap with respect to the test mass identical to what we have in the GRS. So all the electrodes have the same size that they have in the GRS. Then they are moved by a set of linear actuators. The electrodes are surrounded by a guard ring, which is connected to ground, in order to shield or to delete the crosstalk between the different electrodes. So the electrodes are supported by non-conductive support, for instance, made of a ceramic material, and the other are conductive material, like aluminium, for instance. At the end, we don't have any trouble, or titanium. The size is about 30 centimeters of this bar. Okay, so I will spend some words for the linear actuators. They are very smart linear actuators. They use the piezo step technology developed by physics instrument, and they can. So in this way, they can make a long stroke, in this case about 13 millimeter, with a resolution of few nanometer, and inside they have a sub-nanometer encoder in order to measure its position. So we have characterized the linear actuator, and so we have and we did it with a CIOS interferometer, which has an accuracy well below the nanometer. And then we have observed that in a static condition, the positioning repetibility is below 50 nanometer. And then we have checked also the speed of the actuator. They can move quite at a very high velocity, but then we need accuracy in the step, So, as I was showing you, we must update the position of the electrode with the frequency that could be 32 or 16 Hertz. We have to define in the requirement with LISA. And what I'm saying here is that the requirements for the GRS is a maximum speed of about 15 micrometer per second in translation and a rotation of about 500 microradians per second. By combining this speed, we can expect that we have a maximum speed of about 30 micrometer per second. And so so this means 1 micrometer on each step maximum of displacement. And so we have demonstrated that the actuator is fast enough. So then we have, and this is more recently data, then we have also tested the actuator into a condition more similar to what we will have in our emulation, and so we are moving at constant. For instance, we are moving along a triangle. It's the translation is about 0.5 millimeter at a constant speed. For instance, in this case of about 20 micrometer per second. As you remember, the maximum speed was about 30 micrometer per second. So here we are performing very tiny steps, so each step is about 700 nanometer high in the time that in the periodicity of the loop. So in this ramp is the actuator is moving 6 times faster than 2 minutes. Okay. One. Okay, so I will go very quick. So this is the error that the actuator is making in following this positioning in time, and so you can see that we make an error of about 100 nanometer in positioning, and this is the leading term in the performances of the TME. So I would like to show only that differently from what happens in the GRS, we keep the potential of the amplitude of the oscillating potential of the test mass constant. This is simplifying a lot our system, and we did some FEM simulation in order to compute all the electrostatics and thermoelastics behavior, so we can predict the distortion due to temperature. And so what we have observed is that we have cancelled perfectly the crosstalk between the electrodes, and also we control the temperature in the vacuum chamber that will host the test mass emulator, and so also the thermoelastic strain is not a problem. So I conclude by this. So in this way, all the actuators and all the electrodes are independent from the others, and so we can build by a kind of calibration a LUT transforming the current that we have to emulate. As I told you, we have to emulate an electrical signal for the front-end electronics into the position of the actuator, and this can be done independently for each actuator. And so, since my time is finished, I think I will stop here, but there was nothing more.
So, thanks, Carlo Paolo. Do we have time maybe for a question? So if you have a question, you should come to the center and you can turn this on.
Okay. So when driving with the triangle, you turned it around, and how long did it take to get the inertia out and get it going the other way?
The inertia, so when I revert the direction. This can be...
I couldn't tell from the plot because it was a fairly coarse scale.
No, you cannot observe here the scale. It's too large. If you want, you can observe the case of the sinusoidal. I know that it's in this case the speed is decreasing, going to 0, and so. But it's not that large, the lag. I mean, you see here that we reach an error of about 100 nanometer at the top when we are reverting it. And the error also is decreasing because now we are getting closer. What happens? Getting closer, and so it's okay. It's maximum here, the error, but it's not that dramatical. This curve, it's a kind of derivative of this triangle, because the faster we go, the error, the larger is the error.
Okay, I would propose if there are other questions for Carlo Paolo, you can tackle them in between this session and the public lecture. Maybe we can thank him one more time. So the next speaker is Karin Kruuse. She's from the Albert Einstein Institute in Hanover. And she will talk to us about a test bed for validating second generation TDI and clock noise corrections for LISA.
I hope you can hear me all right. Hi, my name is Karin. I'm a PhD student at the Albert Einstein Institute in Hanover, Germany. And today I'm going to be talking about a LISA testbed that we're currently building there. And its purpose is to test TDI and clock noise removal algorithms on hardware-generated data. So I'm going to jump right into the technical stuff. Here we have an illustration of the interspacecraft, or the science interferometer of LISA. Hopefully by now everyone knows that the base readout is largely dominated by the laser phase noise or laser frequency noise, here, these two terms. And then a follow-up noise that we see in the readouts is the clock noise. So the laser noise couples in from both of the lasers that are forming the link, and clock noise comes from your local clock and it couples in at the phase meter via the beat note frequency. So these couplings in the science interferometer readout are what we want to replicate in the lab, including the real time delay. And so obviously these things have been studied quite a lot in simulations, but we want to build a hardware counterpart to see, okay, how accurate are the simulation models, and to sort of take our results and then translate them into the context of LISA. We need to keep track of what exactly are we replicating and what are we not replicating. So, okay, this is here, this lower diagram is our plan for replicating one LISA arm. So in the center here, you see these electronic delay lines. This is something my colleague Reed just a little bit ago talked about in the Grand Ballroom. So I won't focus on that too much. Instead, I'll focus more on how we get the optical signals in there. So obviously when we have these lasers here, their frequency is about 281 terahertz. We cannot realistically pass that through electronics. So what we want to do is heterodyne these laser fields with our reference oscillator. So here on the photodetector, we sort of just do like a frequency down conversion so that we could pass our signals into the electronics. And this heterodyning here, it preserves the phase noise or the frequency noise around the carrier. So we still keep our noise LISA-like. So then we split the electronic signal, and on the local mixer here, you mix you create a LISA-like photodetector signal. So that's where you get a LISA-like beat note. And then you pass it to the phase meter, and then following the LISA model, this is how we would write down our testbed noise couplings. So the clock noise should be LISA-like. For the laser noise, you do see the reference oscillator noise as well, but if you look at the differentials, or essentially the photodetector readings, these are like proxies for the laser noise terms. So the differentials behave in the same way as the direct laser noise in LISA. So from the perspective of TDI, the laser noise still cancels out without any modifications to the algorithm. Then here is our vision for the full testbed. So we do want to build up sort of a 3-satellite constellation. Each satellite would have one laser, and out of these 3 lasers, one is cavity locked, and the 2 other lasers would be phase locked to the delayed signal from the primary laser. Then we have the 4th laser for the heterodynamic step that I talked about. Independent clocks for each of the satellites so that we could actually test clock noise removal. And then these delay lines where we want to have 2 separate or 2 different delays between each spacecraft. So we would have 6 different readouts. Okay, then I want to talk a little bit about the cavity locking that we plan to do. So as I said, we want to have 2 cavity locked lasers. So the primary laser and the reference oscillator as well would be cavity locked. And the interesting thing here is that they still need to form a beat note that is somewhere below 60 megahertz. That's because of the electronics. That's our current limitation for the electronics. So we have 2 custom ULE cavities. And essentially the plan is to, if you look at this illustration here, if you look at the resonances of 2 of the cavities, we would essentially be looking at these pairs of resonances that lie like close enough to each other within your tuning range of the lasers. So this is a section of the tuning range. The tuning range itself would be somewhere around 30 gigahertz, I think. So we will be looking for these places where the resonances come close enough to each other. Then I'll also touch on the delay line a little bit again, just in case if someone missed Reed's talk. So we use these FPGA evaluation boards or GETs. They have this FPGA chip, and they also have like just a regular processing unit, a tiny computer, and they also have the ADCs and DACs included. So everything that's here on this drawing can be done on one of these boards. So 2 delay lines can actually fit on one board. And the way we use them, before running an actual measurement on the tiny computer chip or on the tiny computer that's also on the board, you can calculate either static or time-varying delays and Doppler shifts based on real LISA orbit data. And you can also prepare gravitational wave signals to be injected. So Reed showed all of this. Then during runtime, your FPGA takes care of the handling of the delay and the gravitational wave injection and also the mixing. And here on the right, I plotted the intrinsic noise that one delay line adds, and it sits below this one link noise that you would expect to see in LISA. So if we want to go to LISA-like performance, the delay line shouldn't be a showstopper. Okay, so we have started integrating the optics with the delay line electronics as well. And one demonstration that we did is locking a laser to the signal coming from, or the noise coming from another laser that has been delayed. So this red photodetector reading and the green one, their frequency noise is shown here. They look quite identical. Of course, this is, like the photodetector readings are dominated by the free running laser noise. But also, if you look at the difference, so just in sort of post-processing, you take the difference of the two readings, you already see these familiar LISA-like dips at the frequencies that correspond to the inverse of the applied delay. And you can also look at the sort of the mixed signal that's going into the phase lock loop that is being driven to zero by the phase lock loop. So from here we can already see that the green laser is following the delayed noise of the red laser quite well, which tells us that we can take our optical signal, put it through the electronics and come back to the optics, and everything seems to be working as intended. Another look at the same data, we can also extract a LISA-like one-way laser noise transfer function. So here the purple line is the calculated or like extracted from the measurement graph and plotted against the model. And here in the corner we can see some additional noise at the higher frequencies that is likely coming from the mixing step here. But yeah, it's currently out of the LISA band. And again, this is something Reed showed, but I just wanted to come to where we sort of stand with the laser noise and TDI right now. We can already demonstrate laser noise suppression via TDI. But this measurement specifically was done with electronic input signals. We can already switch those out for a similar signal coming from the optics or being generated by the lasers. Okay. So now I want to quickly touch on the clock noise stuff as well. So as a reminder, in LISA, you have these sidebands that are, the modulating signal is derived from the onboard clock. So in the sideband readouts, you see these differentials, like timing jitter between the two satellites, and it's amplified by the modulating signal, so sort of amplified by a gigahertz signal or tone. In our case, we can with relative ease just plug in these EOMs as well, modulate our spacecraft laser fields, and get the same coupling. However, the catch is that we are limited to megahertz frequencies because that's what we can get into our ADCs right now. And the issue with using a megahertz signal or megahertz modulation frequency is that the other noises, other phase noises in the sideband measurement will now start to affect your clock correction. So for example, we measured our modulator phase noise, and if we compare it to the LISA requirement for the phase noise that's allowed in the sideband, it's nicely below it, but since our modulating frequency would be let's say about 200 times smaller, we should be looking at a requirement line like this if we want to go for LISA-like performance. And this is something that we probably can't fix with just like the hardware itself. We do have to look into how do we go towards a gigahertz modulation scheme. So we have some ideas how to do it. I will probably not get into them right now too much, but the first idea that comes to mind is just modulating the reference oscillator as well with a gigahertz signal. So you get the sideband beat note already here. So your timing jitter is amplified by this gigahertz, but the readout that we can do here is at megahertz. But this here, then you add another sort of timing jitter into the mix, and you need to take care of that. We have a couple of ideas how to maybe take care of that. This ADC mixing idea is that we still do the gigahertz modulation here, and we increase the ADC range. This isn't maybe as easy as it sounds. And also maybe we could try aliasing, so just still using a higher frequency here and looking at the alias signal. And that brings me to my concluding slides. We've done these things already, but there's lots to do, especially when it comes to the optics.
Okay, I think we have time for a question or two. So I'll bite. I have one. When you go to this test with with an optical component, with a local reference oscillator, so are the beat note amplitudes or the are they representative of the light levels? They're not low light?
No, we're
Okay.
not looking into that because for us, like the shot noise also it couples in at a slightly different
Sure.
location in the chain, and that's something we're not really looking into for now.
Okay, but it is somehow sensitive to the analog electronic delays which come with the photodiode readout, or?
I think so, yes, but honestly, I don't think that's something we would see right now because, I think we talked about the sort of clocks of the delay lines themselves. Will probably.
Another quick question? Okay, if not, we can thank Karin. No, excuse me. Please, Simon.
Hi, sorry, maybe I missed it. The hyperstable oscillator, is it running at gigahertz or is it running at megahertz?
Megahertz. So we have rubidium standards, so the signal that comes out of them is 10 megahertz. So all of the frequencies that we do want to actually use, we have to do the conversion as well.
So you're up converting.
Yes.
Do you know what device you will be using?
Not yet. This is something we're looking into. Actually, Guido recommended your thesis for that.
Okay.
Reading material.
At least 15 years ago, we couldn't find anything that is phase stable enough. We had to down convert, so we started at gigahertz. But I would be super interested in if by now there are technologies that is phase stable enough to convert.
That is definitely something we need to take a proper look at.
Thank you.
So let's thank Karin a third time. Okay, so our next speaker is Francesco Venturelli from the Università di Trento. Francesco is going to talk to us about characterizing the LISA GRS gold-coated test mass electrode housing surface UV photo emission with the end-to-end discharge facility.
Okay. Hello. I'm talking about this facility I built in Trento that is going to be technologically transferred to our industrial partner, which be Italy, for the final testing on the coating on the flight model of the GRS. So let me start a bit further from the coatings. So in LISA, as in LISA Pathfinder, there will be this charge management system that by shining the UV light at frequency, what is this? Okay, at 252 nanometers, it will extract electrons from the gold surfaces and counter the charging on the test mass that will be ongoing due to cosmic rays and solar energetic particles during the duration of the mission. This plot shows the, let's say, what was measured in the LISA Pathfinder, where you can see this system achieved to keep the test mass charge in check along the duration of the mission. So, in particular, the total test mass charge couples with these residual stray biases on the electrodes. As you may know, in the science direction, this is the x-axis, there will not be, let's say, electrical actuation on the test mass, and it will be done in this drag-free scheme with the satellite moving. But anyhow, even if you keep this nominally to 0, there will be some stray bias that will couple to the test mass, and at some point this contribution here will become large enough to overcome the noise requirements. Okay, so how do we want to test this in the line up from the engineering model to the flight model. We want to have this kind of system shown here where you have some DAC and some electronic interface that you connect directly to the electrode housing and the electrodes, with which you can control in DC the electrical configuration of the system as emulating the various AC potentials in space. And then from an electrometer you measure the light or the electrons collected from the test mass by connecting these to the fingers of the grabbing and positioning release system. Okay, this will be nicely integrating with also this other stuff here, which is the outgassing facility, which will be mounted on top of the GRS, to my understanding at this point. And so before the final integration, this gets shipped to the prime for satellite integration. You will make a vacuum here, back-out procedure and so on. You measure discharge and residual gas analysis. Great. Okay, in Trento, the facility looks sort of like this from outside, and this is more a detailed electrical scheme that maybe is a bit confusing. So I have this, which is much simpler. So the principle of measurement is this one. You have some potential generators that set the DC bias on the test mass and the electrode housing and the injection electrodes or the sensing electrodes also on top of this. You have some UV source which is modulated by in-fiber shutter here, and the electrometer reads the overall current with this kind of 1 femtoampere resolution with a few minutes measurements per, let's say, at a fixed electric configuration. Okay, a strip of measurements looks like this, where this blue line is the data as taken from the electrometer. The red line shows when we have light or no light based on the opening or closing of this in-fiber shutter, and the green one is the fit I do to this square wave that then is converting to the photocurrent with some Fourier expansion of a square wave. Okay, then all of this to compare with, let's say, properties of the gold is converting to apparent yield, which is in the end the ratio of the electrons emitted or collected to the photons that are emitted at the end of the optical fiber head. I remember the acronym, great. Okay, this looks like, and typical measurements looks like this. You make a scan in the potential of the test mass, and you measure the current, which is converted here in apparent yield, once either illuminating the electrode housing or the test mass. Great. On top of this, you can adjust the potential of the electrodes in DC. And so, for example, if you take the consideration the injection potentials, in which the light will be pulsed in a sort of synchronized way in LISA, you can do this at the 98 kHz in this apparatus, because the electrometer is essentially a DC instrument. So you fixed a potential of injection which corresponds to fixing a phase, but the electrons don't really care about this because they're much faster than the 98 kHz pulse. And so you can see that by setting the correct potentials, you emulate the same effects you would have in flight, where either positive or negative injection potential makes this discharge curve move slightly to the left or the right in this scale. And at the same time, this can be used to check that the overall yield potential, at first order at least, it really doesn't depend on the local field of the injection potential, but only on the total mass potential. That is, in this plot, the dashed lines are just the zero injection potential line shifted by hand by the same amount we would be expected when you apply the injection potential. Okay? And on the other hand, if you take a lot of these curves and you average them out at the same, say, at a given value of V test mass, you can get this red line of which is the same as having a continuous illumination. Let's say DC illumination over all the period of the injection potential. Okay, another cool things you can test with this is local effects, because most of the light gets shined on some actuation electrodes in the Z phase, actually. And so if you turn one on, for example, you keep this positive while you change the overall potential of the test mass, you change the trajectories of local electrons which never reach the test mass, and so you change the position of the amplitude of the curve. On the other side, you can do some other changes with the negative potentials. Okay. Since the facility is pretty static, you can repeat these measurements with some fine enough temporal, temporal resolution, and you can check how this changes when you put the system in vacuum. This is particularly interesting, especially in the first days, I would say, of these measurements, because we are a bit conscious about the fact that handling these coatings is not as straightforward, and there's no like very clear procedure that will guarantee you that a coating made with the same machine is handled in the exact same way from the same people and the same contaminants get into your vacuum chamber. But if you do these kind of measurements and they are somehow consistent, we are happy enough. Okay, so on my last slide, I will summarize again that this test will be conducted at the end at the level of the engineering and qualification and flight model of the GRS by our industrial partners, I think starting from this winter, autumn, winter. And then this, and I would say some same sample, okay, this is one of the tests we have on the coating. The other closer enough test is with the witness sample that will be in the vacuum chamber where they coat the test mass and the electrode housing, and will be done by University of Modena with other techniques on small samples. They also will do some like spectroscopy of the sample surface. And in the end, I leave you here some colleagues that will talk in the next days. Especially, I think this is closely related to the thing that we have also this Augustine facility in the same facility in the end. Okay, that's it.
Thank you, Francesco. Do we have some questions?
Thanks for the talk. You can go on the previous slides, because I'm not sure what is the message of this. Because you say if they are consistent, you are okay.
Yeah,
but I see it's not very consistent.
Yeah, okay. I mean, they're consistent in a way that if you measure, okay, these three are not very consistent for multiple reasons. One, I would say the environment of the laboratory in September was not under control, because we were like at the limit of summer and the AC was not very consistent. And then I think this integration here, especially the Christmas one, it was much faster than these two. I think in these two I kept the electrode housing under test in air for some days, and in this was like some hours. So this changes a bit. And yeah, and in the mean, I think and what I mean by consistent, I think more that if you have a similar time scale of this kind of behavior, you should be happy that you don't have introduced too strange contamination in the system when you are like taking it out from, let's say, some containers you have from the coating company and you put it in the GRS.
So in this case, the conditions were not
clearly under control. Yeah,
okay,
that's what I mean.
But
Go ahead.
So can you go back a couple of slides? Maybe more. There, that's good. So when you change the sign of the voltage, the yield became negative, which I presume is a current running in the other direction.
Yes.
Is there a chance that some of the light is being reflected off where you're sending it and hitting the other electrode?
That's exactly it, because when you, maybe this is easier, this one. So if you think of this, when you have the, Okay, also, okay, maybe it's not the greatest idea, because these are different surfaces. This is on test mass illumination, so, okay, you can imagine that if you shine light on the test mass, when the test mass is very negative, you're repelling most of the electrons, and so most of these are actually going away from the test mass, and so you measure the positive current, and on the other end, you have this on the other side. Why this is not symmetric is probably either some of these are lost on the angles of some trajectories, or light is just reflected to the electrode housing and then they are emitted there, and if they are emitted in the gaps between, like, these gaps, maybe they are not so free to come out to the test mass.
But definitely there are reflected beams illuminating both surfaces.
Yeah.
One more? Okay, if not, we can thank Francesco. So our fourth speaker is from Institute of Space Sciences in Barcelona. He's Daniel Serrano Rubio, and he will talk to us about long-lived sub-millihertz glitches in LISA Pathfinder near the heliospheric current sheet crossings.
Thanks for the introduction. I hope you hear me well. Okay. I changed the title a little bit after a discussion with Katia because it was maybe too indirect on the topic. But basically, these are the last results of my PhD thesis, and I'm not really an expert on the topic. It was just a small part. So what I will be presenting is this. By the way, is not a gravitational wave. What I'm trying to represent with this purple surface is basically the heliospheric current sheet, which originates from the sun. And what we did is study this structure with the real data from LISA Pathfinder as a demonstration for the LISA mission, and to test if we can also use that to investigate this structure. And additionally, we want to see if there is maybe a correlation with the spacecraft crossing this structure and the long glitches that were observed in LISA Pathfinder. So, without further ado, I don't think there is a need to make an introduction on LISA Pathfinder. We already know the performance. So I will just mention that the results that I will be presenting took place in Lagrange point 1, in this orbit here, where the nominal operations of LISA Pathfinder took place. And for the case of LISA, the investigation, if we did the same investigation, would take place here at 1 astronomical unit. So the way that we are going to do this study is making use of the sensors on board the LISA Pathfinder mission. And for example, I will be saying that the sensors are part of the Spanish contribution to LISA Pathfinder and to LISA, and where we include thermal sensors. As we can see here, these are some examples of the thermal sensors that were on LISA Pathfinder. We also include magnetometers and injection coils for LISA Pathfinder, audio bands in LISA, audio frequency sensors, a radiation monitor, more details on that on the parallel session on Thursday by Marina, and we also had the data management unit, no longer the case in LISA. So what I will be presenting will be done with the study focusing on the magnetometers, are these 4 triaxial flux gates that we have here, and I want to highlight that they are platform magnetometers, which, as we can see in this image, basically the magnetometers are placed inside of the spacecraft. Normally, when you do this type of investigation of the interplanetary environment, you use, here I put an example of wind, you have your magnetometers placed on a boom in order to get the spacecraft environment more easily subtracted from your measurements. So, what is the heliospheric current sheet? Imagine the solar axis rotation, the sun rotating in vertical, the black line, and you have your sun as a magnetic dipole, and it's rotating as well, but it's not aligned with the axis of rotation. In that case, the equator of the magnetic dipole will be tilted and will be oscillating, providing this shape that we can see here, which resembles that of a ballerina skirt. If they were aligned, it would be just a flat disk, more simple. What's important about this structure is that it reaches all the way to the end of the solar system, Jupiter and beyond, So this structure, and everything in the solar system crosses this structure at least twice per solar rotation. That is, you cross it once every 10, 14 days. And that's something that could affect your measurements in LISA Pathfinder and LISA and any spacecraft that you have. So also the second objective that we have is the glitches in LISA Pathfinder, of course. So we already know that they affect the performance of the mission, and we try to focus on the glitches that have very long durations. In this case, I show an example of a glitch that lasted for, in this case, it was 3 hours or something like that. And for now, the only possible mechanism proposed is outgassing. Some particles that were stuck somewhere, and during some noise runs, they escaped somehow, some maneuvering, and they kicked the test masses and created this impulse and made this glitch. So our goal is to see if there is a possible explanation behind this with this structure. So to do this, what we do is we combine data from ACE and WIN, because I didn't say it before, but obviously LISA Pathfinder was not a specialized mission for interplanetary investigation, so we lacked many of the key instruments. So what we do is a multi-spacecraft analysis, including ACE and WIN data, and I show them here. In orange, we have ACE data. In blue, we have the data from WIN. And in green is all the measurements that we could obtain from the magnetometers of LISA Pathfinder. Obviously not the spectrogram. The spectrogram comes from WIN data. And on top, I included the delta G, in this case from the noise run of April 2016. Here we have the same glitch that I showed before. And in this case, to characterize one crossing, which are here the dashed black lines, what you typically do is see this sudden change in the polar angle and azimuthal angle of your magnetic field. The main reason is that the surface that is the current sheet is separating the magnetic field lines that escape the sun and the ones that are inward in the direction of the sun. So every time you cross this structure, you go from one direction to the other. Sorry, my apologies. Here, and you get this sudden flip of your magnetic field direction. It's this way that we managed to identify a total of 18 crossings during the whole mission of LISA Pathfinder. Note that here I only show 50 segments, because obviously LISA Pathfinder had a total of 80 segments where we took data, but there were experiments. So we didn't use segments where experiments were being performed. So in total, 180 days were analyzed, and we found 18 crossings. It's consistent with the once every 10-day crossing. So what these dates have been obtained with, as I said, combining spacecraft data, and we want to find a more precise timing of the crossing. And to do so, we record to this hyperbolic tangent rotation model that was proposed by these two publications, which basically assumes that your current sheet, sorry again, here, when you cross this structure, your magnetic field changes following a hyperbolic tangent function. And this happens in a local frame where you define this direction of the current, of the normal, and everything. And obviously, we want to study in the geocentric solar ecliptic plane. So what is done is make these two rotations, an alpha beta rotation, in order to convert your local frame model to a GSE reference frame. And here I have all how we convert it to a time domain. And also I want to highlight this direction. It's for the current. If you apply the Maxwell equation to this model, you can see that you have the currents flowing through the heliospheric current sheet go in the direction of Y and Z, and they don't go in the direction of the sun. So that's interesting, as we will see later. Using this model, we fit the magnetic field data for ACE, LISA Pathfinder, and WIN. We can see that the magnetometers show more or less consistent shapes of the measurements at different frequency samples. So obviously, every mission had different cadence. And using this fit, we obtain the main parameters of the heliospheric current sheet. the inclination, the crossing time, the exact crossing time for each spacecraft, and also the width of this structure. I hope I'm on time, more or less.
Yeah, you have about 4 minutes.
Oh, perfect. Well, not perfect, but okay. So in the end, we are able to extract the two main parameters of the current sheet. For example, the half width, which is basically how big is this structure. It's around 10,000 kilometers, which is consistent with the previous findings in the literature. And not only that, it's also consistent between a spacecraft. And we can also find the current amplitudes. They are not typically reported in the literature. And they follow this trend as expected from the model. And do you using more current, the thinner you are, and vice versa. And what we also want to see is if we are able to predict when crossings happen. Because for LISA, for example, it would be great to know when a crossing is going to happen. If we have a sensor in L1 and we have LISA around here, if we can see when a crossing will happen, if there is an effect. So we studied the delays between the three spacecraft using the results that were inferred from the model, and also by using the orbits that they were. Here I show, for example, the normal that we found, and also the three, for the case of the long glitch, the places where they were, and we analyzed the delays. And we saw that we were not able to recover the expected delays from the ones that we measured, and this could be attributed to a couple of things. First of all, the model assumes a planar heliospheric current sheet, and that's obviously not the case. Also, we are assuming we have different frequency samplings, and also the model is very simple. It assumes an infinite surface. Lastly, now the main point, glitches. So what we did here is the same long glitch as before, which was coincident with a heliospheric current sheet crossing. We converted the delta G from the LTP reference frame, the x-axis in the LISA Pathfinder, into the GSE reference frame, in order to match with the currents that we were measuring, which, by the way, it's expected to have no delta G in the x direction, which is the direction pointing towards the sun, because that was the direction that the solar panels were aiming. So it's very coincidental that we have these currents following in the same direction as the test masses. So we have the hypothesis that maybe if the currents are aligned with the test masses, you can get a glitch, and some other times you don't. But the issue is that we found that the Lorentz force attributed to these currents is of the order, you cannot see it, giottonewtons, many orders of magnitude below the noise itself. So there is no way that's the cause. And also there is this delay, as we can see. If it was in charge of the impulse, it would be around here. And lastly, why sometimes we see a glitch and we sometimes don't see, if that's really the case. That's something that we tried to analyze for all 12 cases. And what we tried to do is say, whoops, here I am. If it was indeed, for example, you see a glitch when you are aligned with the normal, or with the current flow, or with the direction, the change of direction of the magnetic field, or with if you're aligned with the Lorentz force. And the issue is, obviously, we have very few statistics. We only have 3 coincident glitches with crossings and 9 non-coincidence. And we did this analysis, and we saw that there is no difference between having a glitch or no glitch. So we are not sure if it's maybe, at least we can discard with the data that it's not a problem of alignment and orientations. And so with this, I leave the conclusions of the results are the same that I was mentioning, but basically what I want to say today as a main conclusion is that we can use LISA Pathfinder and also LISA in the future LISA mission as another opportunity to do science beyond the typical science that is always mentioned, gravitational waves and things like that. We can investigate the interplanetary environment, and also at a geometrical level. I put here, not to scale, obviously LISA, and we can see maybe the shapes of this and even more things in the interplanetary environment. So thanks for your attention. I hope it was in time.
So do we have a question for Daniel? Yes, I think we do.
I think we do.
Hi, yeah. Thanks for this analysis. I'm interested in it still. I'm curious. What is roughly the time scale for the, like how often would LPF pass through a current sheet? That's probably relatively regular with just a little noise based on the institute.
Yeah, it's the same for every spacecraft. It's the fact that the sun is rotating, and every time it rotates,
But like roughly say every couple days, every couple hours, like what's the cadence for crossings?
once every 10 days, at least
Okay,
from
10 days?
from what we found.
Okay, that's interesting because I mean the nominal LPF glitch rate was roughly weekly-ish or something.
Yeah.
But there were other things. So we could talk from here because I guess there's not a lot of time.
I think there's time for one more question if we have one.
Given the size of the spacecraft constellation, and I'm not entirely familiar with how big the Helio sheet is, when it starts to cross through, does it hit like different satellites at different times? Is there like enough of a delay that you might get a response that would like appear in one satellite, part of the TDI channels, but not all three at the same exact time?
The study for LISA, I haven't done the study for LISA, but for example, that's why this study was helpful here. Even in this case, we have minutes of delays, and assume here it's 2 million kilometers. Just this scale is 10 minutes of delay. Imagine the LISA arm is like even beyond, it's like around here. So if we place one spacecraft here and the other one here, we would expect a delay of 30 minutes. But the issue is that the spacecraft are, the location of the three spacecraft is outside of the ecliptic plane, so maybe they cross at the same time. It will be depending on the normal that we find.
Sure.
Yeah.
Okay, thank you.
Okay, we could thank Daniel again. If there's any more questions for him, you can grab him coming out of the lecture hall. So our next talk will be by Ricardo Waibel of ITP and Heidelberg University.
Thank you very much to the organizers for giving me the opportunity to give a talk here today. So this is also kind of the result of my work in my PhD, and this is basically an application for the dynamics of the LISA satellites, specifically to tilt-to-length coupling.
It should be down.
Oh, down. Okay, sorry.
Yeah.
Perfect. Thank you. This is all in this archive publication that will also be like a proper publication pretty soon. I just basically wanted to show you the constellation with all the naming conventions, which are not terribly important for the talk because I will not be using many formulas, but nevertheless. So we have our three spacecraft with 2 MOSAs each. And in these dynamic simulations, what we basically do is we have all these reference frames, for example, the spacecraft, the MOSAs, and the test mass in the MOSA, and they can kind of move freely with respect to each other. We can simulate all these kind of jitters, and we want to describe tilt-to-length coupling based on this dynamical simulation. What actually is tilt-to-length coupling? I mean, it's kind of in the name. So if you have, for example, an incoming laser beam, and here you have basically the photodiode that measures this, and you are interested in the longitudinal readout of this thing, and here is the pivot point of this photodiode, and if you then have, for example, an off-center beam, and you imagine you kind of change the angle here, you would actually get a longitudinal readout just by the change in tilt of the photodiode. This is one of the ways that you can have this tilt-to-length coupling. Well, within LISA we care about length measurements, and because of this coupling we also need to care about tilt. So if you think in 2 dimensions, you can actually have these 2 degrees of freedoms, but in LISA, along one line, we separate contributions from the receiving and transmitting spacecraft. So we actually have, along one laser link, we have these 4 coupling coefficients denoted by these Cs, and then the angles and the delayed angles here. So we have 4 coupling coefficients, we have 6 laser lengths, so in the end this would be like a 24 parameter model to describe LISA tilt-to-length coupling. I will go slightly more into detail later on this model, but first, how can we mitigate this? This is from the paper of Gudrun Manner et al. And I mean, firstly, we should carefully align all the components on the optical bench, which I mean, there's requirements for that, and they will do anyway. The second thing is, if we actually have some kind of clue what the coupling coefficients are, we can actually basically recenter the beam on the measuring photodiodes with the so-called beam alignment mechanism, so we can actually reduce tilt-to-length coupling if we see that this is kind of large in the data stream, and like last of all, we can also just remove it in post-processing. This is kind of like the mitigation strategy that is mostly planned for currently, because after we subtract laser frequency or phase noise, CTL coupling effects and clock noises are kind of like the dominant things that are believed to be a problem. What we see here is an ASD of the total instrument noise, because I wanted to show you what the effect of TTL is if we look at this dynamic simulation. So this is not a sensitivity curve, because in the sensitivity curve it would go up here again. This is just an ASD of the total instrument noise. So if we then, for example, add this kind of like typical coupling constant of 2.3 millimeter per radians, you see not really much changes. This is because the angular jitter is actually quite low in the dynamic simulation. But then if we increase the coupling coefficients, they actually become noticeable in a specific frequency band, kind of roughly between 7 and 200 millihertz. Knowing that, I will go slightly more into detail. So I use LISA Node, which is one of the simulation softwares, to get kind of these noise curves, and implemented a dynamical simulation for that. And then in the end, there's like a small workflow that I will also go into slightly more detail, bless you, to actually infer these coupling coefficients and then subtract them in the end. So for the LISA dynamics, this is kind of based on an earlier work together with Henri in 2023, where we kind of have this control loop. So we kind of start with the system dynamics formulated as equations of motions. So we have just a state vector, for example, the angles and the positions of test masses. We just evolve this for a time step. Then we perform simulated measurements, which are receive dedicated noise models. Then this goes into the defects controller, which gives a signal to the actuation, which is then basically a force output that receives a noise model again, and then this force is used in the next time step as an external force in the equations of motions. These control transfer functions are from a previous publication by Henri from 2022, and we also have like other ports that we can use to probe the system. I just briefly wanted to show that we have all these kind of different frames. So for example, we have the B frame, which is for the spacecraft, where we basically track the attitude of the spacecraft, and the same for the MOSA frames, where we have 2 of, and they're kind of tilted to with respect to each other. Yes. How do we actually get information about the angles? Because we need the angle or like the attitude information to be able to subtract TTL in the end. And we actually get this from these quadrant photodiodes. So if you have 2 beams, like a reference beam and a measurement beam, coming on top of these quadrant photodiode, because of the tilt, there will actually be like a slight phase shift between the different quadrants, and from that we can actually infer at the angle between these 2 beams. And we perform like a simulated version of this in this measurement block here. So we have the actual angles just from the physics knowledge, which are our internal states. Then we perform the measurements with the noise, and these are then the sensing outputs. But we should always remember that we are in a closed loop scenario, so the noise can also act as a source in the next time step. If we then look at this, for example, these are the jitter curves, or like the ASD of the angular jitters of the spacecraft. So we have the fall off to high frequencies due to inertia, and here the plateau is actually because of the readout noise that then gets coupled into the physical states because of the defects. And down here we see the jitter of the telescopes, which is quite subdominant in the way we model things. In LISA Node, we actually work with frequency changes and not with phase changes. So that kind of implies that we have to work with the derivatives. But this doesn't matter much, except for that our basically measurement noise is not white anymore, which is slightly annoying for the inference step. Anyway, so the TTL model is the one that I showed earlier. The angles that kind of factor in here are the angles between the incoming wavefront from the distant spacecraft and the actual reference beam. So for the phi direction, which is, okay, if you look from the top on the spacecraft, it's kind of this angle. This is just the sum of the spacecraft and the MOSA angles. And for the eta, which is kind of like the up and down tilt, there's also like a factor of the briefing angle in there. So for the inference, we just use the sensing outputs and not the physical states, which we don't have access to in the actual data in the end. And we extract all of these quantities from the control loop. As kind of specified in this publication by Vanna et al., we only consider the TTL coupling for the interspacecraft interferometer. So basically, we don't look at the tilt length coupling in the test bus interferometer, where it could technically also take place, but it is expected to be subdominant. So now that I've shown you how we kind of like generate the data, what we then do to estimate the coefficients is we actually propagate things through TDI, where we just use the second generation Michelson variables. We do the same with the DWS outputs, where we compute the effects on TDI. We use a bandpass filter to basically get the correct frequency range of the data for fitting, because we do this in the time domain, and then we can infer the 24 coupling coefficients. We do that with the least square fitting, which is kind of like the simplest thing you can do. You could also become more fancy and do LCMCs, but in the end it's not necessary. 1 minute, okay. Sorry, then I was way too slow. So we used the least square algorithm, which is quite well known. And in the end, if we have this increased kind of TTL coupling, we can fit the parameters in kind of like a 10% range. Subtraction works well enough that is below the requirements, but we would like to do better. The way we can do better is if we actually add maneuvers, which is like specific excitations of the spacecraft to excite these kind of coupling constants. These were proposed by Henry Wegner of specific frequencies. And if we implement them, we actually get to like 0.1% of relative errors in our coefficients. So things work really quite well. We can investigate them for several effects for amplitude and duration of these maneuvers. But in the end, the takeaway is that even with a full dynamics implementation, we get more realistic jitter shapes. The TTL coupling impact is limited to this kind of frequency bands. We can use the least square estimators. It is a biased estimator for these non-white jitters and noises, but the amount of bias can be kind of well estimated, and it's usually not a big problem. And even short maneuvers, so specific rotations in spacecraft and MOSA, can improve the TTL estimation quite drastically, so we can reliably subtract this from the data. Thank you for listening, and a big thank you to Augie and Sarah for kind of like co-supervising me in this work. Thank you.
We have time. We have time for a question or two for Ricardo.
Thanks for the talk. And I was curious about this maneuver because we did maneuvers in LISA Pathfinder and they was not totally successful. So have you tested this on those data? Maybe I mean the maneuver were in order to subtract this stable coupling. I don't remember if it was tested on that.
So I haven't tested this on LISA Pathfinder data because the TTL coupling is there in the interspacecraft interferometer and not in the local interferometer. I'm not sure how much these maneuvers basically carry over, but yeah, that would be kind of interesting to see whether we can kind of get close to these kind of things.
The principle should be the same, but I remember during the operation it was not working. But maybe I think that Gudrun and Zara find the right way to. So it could be different in this pattern, even in LISA, even more complicated. So I want just to see.
Yeah, so I mean, this work by Henry was together with Gudrun and Sarah. So from all the simulations we've done, it works quite well. I think they also tried a similar, or we're planning to try a similar thing in the Grace follow-on mission. I'm not entirely sure what the status is of that, but.
Okay, thanks.
So we just real quick have one last question, which was online.
Okay.
And the question I think refers to a few slides back. And the question was.
Sorry, that was exactly the wrong direction. Yeah.
The question was, what do you think the jitter levels, so the angular jitter levels, will be realistically? So I guess this is based on either required or some simulated values. And the question was, do you have any more information as to what the realistic jitters will be? And yeah, I think it refers right to this.
Yeah. I mean, on some level, we don't know. I mean, we try to be most realistic so basically the input noises are the ones that we know from requirements. We covered all these kind of things, but specifically a large impact is kind of how the defects is implemented. And this industry will determine, and I mean, so the defects here is optimistic on some level, and like the modeling is a little bit older, so this will definitely have an impact, but we kind of expect it to be roughly that.
Okay, I think that's fair. We know this is something which is in the hands of industry, and at some point they'll give us their estimates of what this will be, and we may or may not be free to discuss it. But so let's thank Ricardo. And I'll call up our last speaker, who is Tiina Minkkinen from the University of Helsinki, who will speak to us about recovering gravitational wave signals in simulated LISA data with non-stationary instrument noise.
Okay, thanks for the introduction. I'm presenting work on behalf of all of us listed here. And first, shout out to the Munich Institute for Astro, Particle and Biophysics that brought us together to work on this topic. And as I'll be talking about the LISA noise, specifically the non-stationarities in the noise, I thought it's appropriate to start with an introduction to what I believe is to be everyone's current favorite LISA instrument noise model as far as data simulations and analysis goes at the moment. So we have these two noise components, the OMS noise and the acceleration noise. So the OMS, the optical metrology system, is what tracks the position of the test mass inside the vacuum chamber. And the noises related to this are most dominant in the high frequency range. And then the test mass noises arise from the spurious accelerations of the test mass. And I think yesterday and yesterday we heard many talks explaining different mechanisms of how these accelerations come about. I'll be talking about one of them, and these types of noises are most dominant in the lower frequency range. Then when we move on to the TDI domain, so we combine the measurements from the different interferometers, we get these sines and cosines giving us the familiar wiggles and the zeros at the higher frequencies. Here you see the TDI channels, the noises for the TDI channels A and E, which are the noise orthogonal channels. And our final noise PSD is just the sum of these two components. And this is the noise model that our work is also based on. We are going to make it slightly more interesting by taking into account that the noise doesn't remain stationary throughout the mission lifetime. Here are just a few effects, few things causing non-stationarities in the noise. We have gaps and we have glitches, and we don't necessarily expect that the noise levels will remain the same after these gaps and glitches. We have the extra component of the galactic binary foreground that is annually modulated, so it goes up and down during the year due to the isotropic nature of the foreground. And then we have this Brownian noise from the test mass that will be decreasing over time, and this is the component that we are most interested in this study. So where does this Brownian noise come from? Well, the test mass is nominally free-falling inside a vacuum enclosure that is vented on Earth before LISA is launched. But this venting procedure will not create a perfect vacuum. There will still be some residual gas in the vacuum chamber as the satellites are launched. And what we saw in the LISA Pathfinder is that as the mission goes on, the gas will escape. And here you see two measurements from the LISA Pathfinder, probably a very familiar figure to all of us here. But anyways, the blue curve is the measurement from the noise right after the launch, and the orange curve is the noise about a year from that. So we see that it has gone down quite significantly. And here is the decay plotted as a function of time. And we can parameterize it by A, which is the nominal noise level at the beginning. We have gamma and we have TV. TV is the time from the initial venting of the vacuum enclosure. And then applying this factor to the test mass component of our noise and plotting it for 1 year, this is our evolving noise model now. And next we want to see how this affects signal detection, how we can mitigate this effect, and if it can actually be useful for us. To do this, we start by simulating non-stationary instrument noise using the LISA instrument, or a slightly hacked version of the LISA instrument where we added this factor in to multiply the acceleration noise component. We simulate 1 year of data, and this simulation is done in time domain, and we chunk the time series into 12 one-month chunks so that we can then fit a separate noise level into each chunk. Then our signal here that we are looking at is a verification binary. We use FastGB to simulate this because it's fast. And this simulation is done in frequency domain, actually. So to combine these two signals, we transform our instrument data into frequency. And here in gray, you see the narrow band where this binary signal will go into. And here is an example chunk of the final data that we will be fitting our model into. And then we formulate our likelihoods. We will look at the signal recovery in 3 different cases. At first, we assume that the noise actually remains stationary, although it doesn't. We fix the noise level to the nominal level, so the level at the beginning of the data. In the second case, we model for the non-stationarities, but we assume that we know that the noise goes down according to the LISA Pathfinder fit. And then in the last case, we let go of this assumption of the noise levels going down as injected in the data, but instead we also try to infer them. And to do this, we do an MCMC. With MC, we get these probability distributions of the most likely parameter values given our model. And here you see just the binary parameter values. This is the first case where we fix the noise parameters or the noise levels. And this is for a stationary noise assumption. The blue lines here are the fiducial values, so what is injected into data. Here it actually looks like it's recovering the binary pretty well already, although our assumption of the noise is essentially wrong. But that's because the signal that we have injected is very loud. So even though the noise assumption is wrong, we can still see something. But when we move on to modeling for the non-stationarity, we see that our posteriors here are already getting quite a bit narrower, so we are becoming more certain of the signal. And then in the final case, where we also fit to the noise levels, our binary recovery looks pretty much the same as in the case where we fix the noise parameters, the noise levels. And here on the right, you see the recovered noise levels plotted against the true values, so what is injected in the data. There is some fluctuation in here, but that is because we are looking at just one noise realization here. And there is randomness to the noise that comes out from the LISA instrument. So that would explain the noise levels that are a bit far from what we inject in the data. And then to become a bit more certain that we are seeing what we think we are seeing, we also plotted we created 100 different noise realizations, and we ran the MCMC in each case, and we plotted the sigma variance as histograms for each of the parameters. And here in orange, you see that these are the ones where we have the narrowest posteriors, so the most certain results. That is the one where we model for the non-stationarity and fix the noise parameters. I think it's pretty much expected that that one performs the best. But what is nice to see here is that the one where we also infer the noise levels, we are not far from the ideal case. And then the one where we falsely assume that the noise is non-stationary, in that case we get the widest posteriors, so we have more uncertainty. And then what we want to do next is, of course, a bit more testing, a more robust statistical model comparison, for example. We also want to try and recover a different type of a signal. So here you see a phase transition from an early universe phase transition, a stochastic background from that, and that is a wider band signal, slightly lower amplitude, or actually a lot lower amplitude compared to the binary signal that we have. And to recover that from the data, we would have to also let go from our assumption that the noise level in each chunk is constant. So we would have to build a better, a more accurate noise model in that case. And another thing that we have been poking at a little bit is a comparison with the wavelet domain methods. And here you see a cool plot of the non-stationary noise, how that looks in time and frequency. And for this, if you have any questions about this, I suggest that you direct them at Robbie Rosati, who is our wavelet domain expert. And yeah, that's it for me. Thank you for your attention.
Okay, do we have any questions for Tiina? So I have a question. Well, actually, one comment. So we hope to give you we work on the GRS, so we hope to give you a system with a lower pressure, and as the pressure goes down, it changes much more slowly.
Okay.
But that said, it looks very important to be studying cases where, in general, you have noise which isn't constant. I just want to understand, in your inferred analysis, where you inferred the noise levels, were you inferring a noise level for each chunk?
Yes.
I see. So you don't have, like, let's say, a model for how the noise is going down, but you assess the noise level piece by piece.
Yeah. So in our model, we have the model for the binary signal, and then we assume that in addition to the binary signal, there is some noise in the data, but the noise level is just constant. So yeah, in each chunk it can be anything, but it's just a constant value.
And is that just for the acceleration noise, or did you also infer, let's say, the optical metrology noise as well?
Yeah, so this sort of, here we are not using the noise model that I introduced before, so we are just, oh, sorry, wrong way. So this noise model here is not actually what we are inferring in this case, but it would be when we move on to inferring for example, the stochastic background, where we are dealing with a wider band.
I see.
So in that
your
case,
binary
we would
case,
have to, yes,
we would,
yeah, in the binary case, it's just such a narrow
I see.
band that we can assume that it is just a constant level.
But when you go to a stochastic background search,
Yeah, then we would have to apply this into our likelihood.
okay,
Yes.
thank you. Do we have any other questions for Tiina? Okay, otherwise we should thank Tiina and all our speakers.